Chapter 9, Geologic Time. Creating a timescale, the relative dating principles. The importance of a timescale. Rocks record geologic and evolutionary changes throughout Earth's history. Without a time perspective, these events have very little meaning. Numerical and relative dates. Numerical dates specify the number of years that have passed since the event occurred. For example, the limestone is 250 million years old. Relative dates place a rock in sequence of formation. For example, the Hermit Shell is older than the Coconino sandstone. Okay, for relative dating, we have certain rules we use. One of them is the principle of superposition. In an undeformed sequence of sedimentary rocks, each bed is older than the one above it and younger than the one below. This principle also applies to surface features like lava flows and beds of ash. This is what I call the layer cake principle. So superposition, so here's the Grand Canyon. So the rock layers down here are the oldest, and this one's a little bit younger, and this one's a little bit younger. Up to the one at top is the very youngest. Principles of original horizontality. Layers of sediment are generally deposited in a horizontal position. Rock layers that are flat have not been disturbed. Third rule, principle of lateral continuity. Beds originate as continuous layers that extend in all directions till they eventually thin out or grade into a different sediment type. So here, these rock layers, they're not very flat right now, but when they're originally formed, they are formed in flat layers. So these rocks haven't been disturbed by compression. Lateral continuity. In the Grand Canyon, see, this rock layer here is the same as this rock layer here. It's just, it was all laid down all over this region, but a river has carved through it. Principles of cross-cutting relationships. Younger features cut across older features. Inclusions. Inclusions are fragments of one rock unit that are enclosed within another rock unit. The rock containing the inclusion is the younger one. So here we have the rock here that has a dike that's formed cutting through it. This dike is younger than the rock it passed through. Unconformities. Okay, the rock layer, the rock record's not complete. There are times when the rocks were exposed and eroded away, and the layer subsided and new rocks laid on top. And so unconformities are gaps in the rock record. Okay, so layers of rock that have been deposited without interruption are called conformable layers. So an unconformity is a break in that rock record produced by non-deposition and erosion of rock units. There are three basic types: angular unconformity, nonconformity, and disconformity. Okay, so here we have an angular unconformity. The rocks here are tilted up, and these rocks are at a different angle. So this is an angular unconformity. Okay. So angular unconformity, tilted rocks are overlain by flat-lying rocks. A disconformity, sedimentary strata on either side of the unconformity are parallel. So you got horizontal rocks and then more horizontal rocks. A nonconformity, sedimentary strata overlays metamorphic or igneous rock. All three types of unconformities can be seen in the Grand Canyon. So here, the diagram of a portion of the Grand Canyon. Okay, right here we have a nonconformity because the sedimentary rock is laying on top of igneous or metamorphic rock, actually metamorphic rock. Here, these sedimentary layers are on top of metamorphic and igneous rock, so it's also a nonconformity. These rocks are at an angle to these rocks, so here we have an angular unconformity. Okay, here we got horizontal sedimentary rocks and then horizontal sedimentary rocks, so this is a disconformity. Okay. Now, applying the principles to figure out which layer is older than the next. Okay, so first, these layers A, B, C, and E were deposited. Okay, and there's uplift and intrusion of a sill. Okay, so here we have an igneous sill came through here. Okay, and that uplifted and ended up between E and C. So D is younger than E. Okay, and then a dike cut across. So this F here is the dike that is youngest. It's younger than the sill, which is younger than these layers of rock. And then these layers were all tilted, okay, and the exposed layers were eroded. So now we have angular unconformity being formed as new rocks were laid down. So G, H, I, J, and K. Okay, and then probably some subsidence, and then let's see, anything else? So finally, then there's a stream valley. Okay, that's going to start creating another gap in the rock record. Fossils are evidence of past life. Fossils are traces or remains of prehistoric life in preserved rock. They are preserved in rock. Paleontology is the study of fossils. Knowing the nature of life that exists at a particular time helps researchers understand past environmental conditions. Types of fossils. Permineralization. Mineral-rich groundwater flows through the porous tissue and precipitates minerals. Example is petrified wood. Molds and cast. A mold is created when a shell is buried and then dissolved by underground water. A cast is created when the hollow space of the mold is filled. Carbonization and impressions. Carbonization happens when an organism is buried, followed by compression, which squeezes out gases and liquids, leaving a thin film of carbon. So that kind of preserves leaves, delicate parts of animals. Impressions remain in rock when the carbon film is lost. Amber is the hardened resin of ancient trees, very effective at preserving insects. And trace fossils are indirect evidence of prehistoric life. They could be tracks or burrows or coprolites or animal dung, and gastroliths or stomach stones that reptiles use to grind up food. So here's a picture of petrified wood. Here's a mold and cast of a trilobite. There's a thin carbon film of an ancient bee. This is an impression of a fish skeleton. Here's a spider in amber, and here's some fossil dung or coprolite. Conditions favoring preservation. Most organisms are not preserved. Rapid burial and the possession of hard parts increases the chances of preservation. Okay, correlation of rock layers. Correlation involves the matching of rocks of similar ages from different regions. Correlation provides a more comprehensive view of the rock record. Okay, so correlation. One, we know that the layers of rock are laid out all along a region in every direction. Okay, so even though there's some breaks here, we can still correlate this white layer to this white layer. Okay, now even though there's a fault here, correlates to this white layer. So we can correlate similar rocks together. Okay, now within limited areas, it's often accomplished by knowing the position of the bed and the sequence of the strata, whilst matching rocks of similar ages from different regions. To correlate over large areas, fossils are used for the correlation. Okay, so fossils and correlation now. Principle of fossil succession. The principle of fossil succession states that fossils are arranged according to their age. So there may be fossils from the age of trilobites, fossils in the age of fishes, fossils in the age of reptiles, or fossils we know from the age of mammals. Index fossils and fossil assemblages. Index fossils are widespread geographically and limited to a short period of geologic time. Okay, so here's some index fossils. Okay, fossil assemblage is a group of fossils used to determine a rock's age. Environmental indicators. Fossils can be used to infer information about the past environments. So shells of organisms can be used to infer positions of ancient shorelines and seawater temperatures. Okay, so here's our fossil assemblages here. So we know, let's say this trilobite lived during this time span. Okay, and then this scallop lived in this time span. Okay, so we have the scallop, we have the trilobite, we have this fern, we have the brachiopod and the starfish. We don't have the leaf or the dinosaur. So where all of these overlap is in this band. So you know this rock had to be from somewhere in this time frame. This rock layer up here has a different assemblage. It has the scallop and fern and starfish, but it also has the reptile and the leaf. So where they all overlap is way up here in this timeline, and they're younger. Okay, now dating with radioactivity, this is where we can try to get actual dates or millions, how many millions of years ago. So first we got to review a little bit about basic atomic structure. The nucleus contains protons and neutrons. Protons are the positively charged particles with mass. Neutrons are a combination of a proton and an electron that have a neutral charge. Electrons are negatively charged particles that orbit the nucleus. The atomic number is the number of protons in the nucleus. Okay, the mass number is number of protons plus the number of neutrons in the nucleus, and isotopes are the same number of protons they have different numbers of neutrons. Radioactivity is a spontaneous decay in the structure of the atom's nucleus. Okay, types of radioactive decay. We have alpha emissions. An alpha particle, which is 2 protons and 2 neutrons, are ejected from the atom. So the mass number is reduced by 2 and the atomic number is lowered by 2. Beta emissions. A beta particle or electron is ejected from the atom. A neutron is composed of electron and a proton. When the electron is ejected, the mass number remains unchanged and the atomic number is increased by 1. Okay, because that neutron now became a proton, right? Electron capture. An electron is captured in the nucleus. Electron combines with a proton and changes into a neutron. The mass number remains unchanged and the atomic number is decreased by 1. Okay, so here, this alpha emission, we have okay, so we have 4 particles, 2 neutrons, 2 electrons ejected. Okay, and beta emission, here we have a proton. That's, we lose an electron, leaving behind a proton. Okay, electron capture, when the protons captures an electron, it becomes a neutron. Okay, now radiometric dating uses the decay of these isotopes in rocks to calculate the age of the rock. Okay, so the half-life. Half-life is the amount of time required for half of the radioactive isotope to decay. Radioactive parent isotopes decay to stable daughter isotopes. Okay, now that they may have to decay to unstable daughters, and those decay into a stable daughter. It might take many steps, but at the end there's a stable isotope. When the ratio of a parent to daughter is 1 to 1, so 1/2 has passed, that's the half-life. Okay, so here we have our number of atoms that we start out with, that's radioactive isotope, and we don't have any daughter atoms. As time goes by, we have more and more daughters and less of the parent. When we get to a 50-50 mix, that is 1 half-life. So half of the parent material has become daughter material. At the second half-life, half of that 50%, okay, so 25% more, the daughter atoms are there, it's 75%, and only 25% remains. Then the third half-life goes by, then 12.5% are increased on the daughter, and 12.5 is removed from the parent. So we have 87 versus 13 atoms, and so on and so forth. Okay, using various isotopes, for each passing of half-life, 50% of the remaining parent decays to the daughter atoms. As the parent atoms decrease, the daughter atoms increase. Several naturally occurring radioactive isotopes are useful for dating rocks. Potassium argon has a half-life of 1.3 billion years. Can date rocks as young as 100,000 years old. Potassium 40 decays to argon 40, and then calcium 40. Argon 40 is a gas and is only present in rocks as a daughter product of the decay of potassium 40. So it doesn't come from any other source, so we know it comes from the radioactive decay. Okay, so here's another example. Uranium 238, okay, can eventually become lead 206, has a half-life of 4.5 billion years. Uranium 235 becomes lead 207, has a half-life of 704 million years. Thorium, okay, 232 becomes lead 208, has 14.1 billion years. Rubidium 87 becomes strontium 87, is 47 billion years. Potassium 40 to argon 40 is 1.3 billion years is its half-life. Okay, so these with a very long half-lives of 47 and 14.1 billion years may not be too useful. Earth's only 4.6 billion years old, but the potassium 40 and the uranium 235 and the uranium 238 may be helpful. Okay, it's a complex process. Determining the quantity of parent and daughter isotopes must be precise. Some radioactive materials do not decay directly to their stable daughter isotopes. For example, uranium 238 has 14 steps till it ultimately becomes lead 206. Okay, so uranium 238 can become thorium 234 to uranium 234 and so on and so forth till it eventually becomes lead 206. Sources of error. The system must be closed. No external addition or loss of parent or daughter isotopes. Fresh, unweathered rocks are ideal for radiometric dating. Earth's oldest rocks can be found on the continent. All continents have rocks exceeding 3.5 billion years. This confirms the idea that geologic time is immense. Now, dating of carbon-14. Radiocarbon dating uses radioactive isotope carbon-14 to date geologically recent events. The half-life of carbon-14 is 5,730 years. Can be used to date events from historic past to events as old as 70,000 years. So this is often something that's used more by archaeologists. Carbon-14 is produced in the upper atmosphere from cosmic ray bombardment. Carbon-14 is incorporated into carbon dioxide and absorbed by plants through photosynthesis. Carbon-14 is only useful in dating organic matter. All organisms contain a small amount of carbon-14. Okay, so here's actually carbon-14 has a neutron capture and proton emission, and then when it decays with a beta electron emission. Geologic timescale, which the geologic timescale encompasses all of Earth's history. It subdivides geologic history into units, originally created as using relative dates. Okay, so for example, okay, we have a large chunk of time called eon, and we can break those down to eras. Okay, these could be billions of years, these eons. Okay, so they get broken down into eras, so billions or millions of years, which then get broken down to periods, which then get broken down to epochs, which then can be broken down into an age. And these still run millions of years. So these are very large chunks of time. For example, the Phanerozoic eon can be broken down to the eras of Cenozoic, Mesozoic, and Paleozoic. Okay? The Mesozoic, okay, can be broken down into the Cretaceous, Jurassic, and Triassic. And then these can be broken down to late and early, or late, middle, and early. Okay, and then ultimately, say the middle can be broken down to the Calovian, the Bathonian, the Bahokian, and the Alienian. Okay, so here's what our geologic timescale looks like. It's actually a pretty large chart. This part here is just a zoom into the Cenozoic here. Okay, so we don't have too much detail. Okay, so here we have the Precambrian, has the Hadean, that's our oldest era, the Archean, the Proterozoic. And here's our Phanerozoic. We have the Paleozoic, the Mesozoic, and Cenozoic. In the Cenozoic, we have the Quaternary and the Holocene. So here's where we are in the Holocene here. Okay. So structure of geologic timescale, an eon represents the greatest expanse of time. The Phanerozoic eon is visible life. It is the most recent eon, which began about 542 million years ago. Eons are divided into eras. Phanerozoic eon is divided into 3 eras: the Paleozoic of ancient life, the Mesozoic of middle life, and the Cenozoic recent life. Each Phanerozoic era is divided into periods. The Paleozoic era has 7 periods. The Mesozoic and Cenozoic each have 3. Each period is divided into epochs. Except for the 7 recent epochs in the Cenozoic, most epochs are termed early, middle, and late. In Precambrian time, most detail on geologic timescales in the Phanerozoic eon. The 4 billion years prior to the Cambrian period are divided into 2 eons, often collectively referred to as the Precambrian: the Proterozoic and the Archean. Proterozoic is before life, and the Archean is ancient. Less is known about Earth further back in geologic time. During the Precambrian, simple life forms that lacked hard parts, algae, bacteria, worms, and fungi dominated. The first abundant fossil evidence does not appear until the beginning of the Cambrian period. Many Precambrian rocks are highly deformed metamorphic rocks. Okay, terminology and geologic timescale. The Precambrian is an informal name for the eons before the Phanerozoic. The Hadean refers to the earliest interval of Earth's history. The geologic timescale is continuously updated. Numerical dates for sedimentary strata. Sedimentary rocks can rarely be dated directly by radiometric means. Geologists must rely on igneous rocks in the strata. Radiometric dating determines the age of the igneous rocks. Relative dating techniques assign date ranges to sedimentary rocks. So dating sedimentary rocks. So here, sedimentary layers. Then we know there was a volcanic ash bed here, and then there was a dike here. The dike we've aged at 66 million years, so we know this is younger than all of these rocks. This rock here must be younger than 66 million years. Okay, and we've divided up, these rocks are from Jurassic, these are the Cretaceous, and this is the Paleogene age.